Hello, everyone. You hear me? Yes, Renato? Yes, thank you. Good job. So welcome to week 14, lecture B. It's Friday again. Don't you guys feel the time is flying? Okay, I'm sharing my screen right now. I hope you can see it. So I'm going to review. We're here today. We are in. Today we are going to go through LVDT, and later part we are going to do the encoders for digital sensor. Okay, you're having fun, I hope. So then next week we are going to do actuator, and I was planning to skip the whole week's class, but I think it's not good. We are still going to do May 5th, the Wednesday lecture, two parts. One part is regarding a lab view and PLC, quick intro. After that, we do the review session. I think you should attend. I will tell you what's in the final exam. I mean, last year's, not this year. Okay, so you got a feeling about what I care about the topics I want to check, whether you have really learned, okay? And then the Friday, for both days, we still have office hours. So the last day, we don't have class. I said in theory. This is a humorous saying. When you say something in theory, then you ask, then what about in practice? In practice, there is no last day of learning of mechatronics. It's a lifelong time learning, okay? So everything I taught you in this class is just very fundamental. So you still have to learn by yourself a lot you need to pick up. Okay, so let's take a look of what we learned last time. Okay, for analog sensors, we first we gone through this we gone through this thing. Okay, so we can use those potentiometers to measure linear, rectilinear motion, or the rotary. Okay, to check the angle. In many of the low-cost solutions, the potentiometer is really the solution. What you need to take care when you use potentiometers as motion sensors, you should be careful about this load effect, like we have seen here. Okay, seen here. So basically, your linearity, okay, x and y. So this is y. Uh-oh, give me a second. So this is y, this is x. Okay, this is x. Let's do the red one. So the y of x is kind of like should be a linear relationship, okay, straight line. But in practice, you will have a nonlinear relationship between this load effect, okay, load effect. So sometimes if you use op-amp to solve that load effect impedance matching problem, yes, but you increase the cost. You need to have a power supply for the op-amp. You need op-amp itself, so increase the complexity of the circuits. Okay. So today we are going to come over here called this is the starting point for today, week 14, lecture B. So motion transducers can use the idea of variable inductance, okay, using the principle of electromagnetic induction, okay, called variable inductance transducer. So the flux linkage between the electric conductor will change. A voltage can be induced, okay, induced. That's why I call it inductor, okay, induced in the conductor. So generate a magnetic field opposed to the primary field. You have learned this thing in the high school, I believe. Okay. So a mechanical force is necessary to sustain the change in the flux linkage. Okay. And so if you have a relative motion change in the flux linkage, okay, due to the mechanical relative motion, so that mechanical energy can be converted into electrical energy. So that's all the basics of electromagnetic induction. And so the principle of the operation of variable inductance transducers. We are going to see a picture of this one. Let's see a picture of this one. So one of this is called linear variable differential transformer. Okay, LVDT is widely used. It's much more sensitive than the potentiometer. Okay. Then overcome most of the shortcomings of those potentiometers. Okay, and it is also a passive transducer because the displaced measurement provides the energy for changing the induced voltage. So sometimes, of course, you need an external power supply, energize the primary coil, which in turn produces steady carrier voltage in the secondary coil. So in general, the RVDT is a variable reluctance transducer of the mutual inductance type. So let's see this example here. So this core is called a ferromagnetic core. Okay, this core can move this direction or that direction, so left and right. But around this ferromagnetic core, we have a cylindric wrap. Okay, so you cut intersection in the middle. You see all the dots here are coils. So these are the coils. Okay, these are also coils. These are the coils. Okay, coils. So depending how you connect the coils, it's called winding. Okay, the windings. So those windings. Okay, so you give the reference signal here. So say, for example, these are the DC signal. You provide to this one, you are going to generate a magnetic field. Okay, so you have left and right. All these the form for the insulating forms. Okay, these are the insulating forms. So basically, you have a coil, and coil. Okay, with many turns. Okay, many turns. Okay, many turns. All right. So then, when you have this is called primary coil, primary. Then you have a secondary. Okay, you also have a secondary, primary and secondary. So when you have the motion in this ferromagnetic core, then those secondary coil. So these are the secondary coils. Okay, secondary coils. Okay, then will generate the induced voltage output. Okay, induced. So this type of working principle for LVDT, the T stands for transformer. There's a movie with the title Transformer, right? So transformer has something like this. Okay, so you have a core, okay, ferromagnetic core here. So then you have a primary coil. So then you have secondary coil. So this is VI, VO, okay, input and output. Okay, all right. So this is called transformer. Okay, primary and secondary. So this is exactly the same, secondary. But the question is, now we are trying to make this guy, okay, I move up and down. So then the coupling will be different. So the reluctance between this primary and secondary will change. Okay, will change. So therefore, that motion will cause the reluctance change. Well, if we keep the VI constant, then VO will change. Okay, will change. So let's check the coil. Okay, so this is a displacement, okay, of that core. So during the small range, okay, I call this is a linear range. Okay, linear range. Then it is linear. So in this range, it's linear. So of course you pull out. So this is 0. That means you already move this. Everything is out. Okay, so you have no coupling almost. So then it's 0, which is reasonable, right? So that is this region. Okay, and also this region. Okay, next side. So there's only limited range that is linear. Okay, that is linear. So if you extend a little bit, so this is nonlinear, then this is nonlinear. So this is nonlinear. Do you guys still remember magnetization hysteresis? Okay. This is kind of like if you go this direction, then go this way, then come back through this way. Okay, so this is called hysteresis. Hysteresis. So because of the hysteresis, this will introduce additional nonlinearity. Okay, additional nonlinearity. But in our case, the range is small, so it is usually very linear. Okay, very linear. So LVDT. So this is one way of using this variable reluctance mechanism to produce the output. Okay, so this is LVDT. Okay, so it has a cylindrical, you have an insulating non-magnetic form. Okay, has embedded into this one as a primary coil in the mid segment, and the second coil symmetrically wound on the two ends of the segments. Okay, so that's actually understandable. Okay, so this is called a differential connection. Differential connection. So if you stay in the middle, then they are generating the same. So there's a no. This is 0. Okay, this is 0. Okay, so sometimes you also call the primary coil as called as a field excitation circuit. So you basically try to give a supply, power supply, and generate a magnetic field. Okay. Then if you have a motion in the core, the bar, this is the bar. If you have a motion, then they will produce the voltage here. Okay. So this kind of connection is called a differential connection. So the middle point is also called a null position. Okay, it's 0. Output is 0. Because of this opposing secondary winding connection. So then if you go left, the voltage will be positive. Then if you go right, then left and right, they have different polarity, positive or negative. So the performance of this LVDT, especially the sensitivity and accuracy, to improve with the excitation frequency. That means the carrier frequency. So that is this guy. This guy. You have a different frequency carrier, and then you produce a different sensitivity. Usually, the higher, the better. Okay. So advantages. Let's make a summary of this. So there's no real mechanic contact, so that you have no friction resistance. So this is opposing to the open of potentiometers. Potentiometer, you do have a friction, so it's almost ideal electromagnetic energy conversion, and it's lightweight core, very small resistive force. Okay, and hysteresis in this case is usually very small. There exists, but it's very small. In this case, output impedance is lower, like 100 ohm. Okay, so it's possible you don't have to use a signal amplification because the generated voltage is higher enough. Directly you can use it, and it's directional. Okay, it's directional, but the range is small. Okay, the range is usually at like a centimeter level. Okay, centimeter level. Okay, so if you have centimeter long, then the travel is about 2 millimeters. So it's a really small displacement, and it's very ruggedized. Okay, ruggedized. It's very robust and inexpensive, durable, and the resolution is usually very high, like 0.1 millimeter level. Okay, so that is for a linear LVDT. Okay, so again, T stands for what? T stands for transformer. D stands for what? Differential. Why we say differential is because of this connection. This is a differential connection. Okay. Okay. Differential connection. V is a variable. Okay. Variable. And L stands for linear. R is rotational. Okay. Rotating or rotational. Okay. So RVDT is the same principle as the LVDT. So then in this case, I have a rotating ferromagnetic core. Okay. So it is used to measure angular displacement. So it's shaped reasonably wide linear operation region is obtained. It's possible. Okay. So let's see some of those figures. But remember, usually you should not expect the 360, right? So it's like plus or minus 40. So it's like, this is like this one, field of view. Think about your eyes. Do you have a field of view? Yeah, that's true. That's why when you have field of view, your vision is limited field of view. That's why you need to do head check when you drive. Okay, you need to head check. So it's because of that. So the same thing here is we have field of view is plus or minus 40 degrees. That's total is like 80 degrees field of view. So this nonlinearity is usually small here. So let me give you an example here. So you have the same thing here. You have the same thing here. Okay, so in the middle, that's a primary coil, and a secondary coil on the left and the right. But here you have pivot point. So you have something you can move. Okay, it's a moving element. This moving element will have a field of view like plus minus 40 degrees. But beyond that, you don't have that linear relationship anymore. So basically the output here, this V0 is this V0, is kind of linear, okay? It is kind of linear in a short period of angle, okay? Linear range plus or minus 40 degrees. Beyond that, it's not. So this is called operation curve, okay? So in here, we have this the coils and the ferromagnetic coil, rotating ferromagnetic coil. So because of its moving, and then the magnetic coupling basically is the medium. Okay, magnetic medium is changing. It's changing. Therefore, the reluctance is changing. So that's why it's a variable reluctance, and it's rotational. And we have differential connection. and it is the basic principle is like transformer. Okay, it's called RVDT. So now you get the idea of LVDT and RVDT. Okay, so let's quickly look just visually other types like proximate sensor. For example, you still have this. This is a primary winding. Okay, this is a primary winding here. Primary winding. Primary winding. So then you have this secondary coil. So you have ferromagnetic target. So you say, for example, this is a wall. Okay, you install some small tape or ferromagnetic thing. So if you close to it, okay, then you start to see whether you are going to how close it is. Then you can detect the output voltage here is proportional, is inversely proportional. Okay, inversely proportional to the distance. So if you are closer, your voltage is high. If you are leaving, then the voltage is low. So we can check the threshold so that this is a limit. I don't want you to hit it. So if I see my voltage is bigger than this value, then I say stop. Yeah. So this is called proximity sensor. How close we are, we can detect that. This is another mutual inductance proximity sensor using that kind of transformer principle. So this is used as a limit switch, okay? Limit switch. Let me give you an example, okay? So you have a power window of your car. So you press the button, the window will go down. But press another button, the window will go up, right? The window glass. So, but you know that once you hit the limit, it will stop. So even you press the button go down, it will not go down anymore. Just stop, no action. So there's some logic circuits there based on this proximate sensor to detect how close we're already hit there. But sometimes, of course, to save money, they probably use the mechanic hit switch. You actually hit something, then you turn on something, right? Or turn off something. Using that on off, you do a logic control, okay, logic control. So in our car, there are lots of something called logic control. So if you hit this, then what? The kind of sequence. Okay. So we're going to learn a little bit. Something called programmable logic control is widely used in industry, especially in those production lines. Okay. So here is an approximate sensor principle. It's also widely used in practice in the mechatronic systems. There's a resolver. Okay, a resolver is used to detect the angular displacement in an analog way. In the next, we are going to talk about how to measure the rotational angle using a shaft encoder, okay, called shaft encoder. Because you have a rotation, then I put on the shaft and encoder. I count how much is the displacement, angular displacement. But there's other principle here is in an analog way. It's not a digital analog way to do a mutual induction displacement transducer. If you have any relative motion between the coils, primary coil and secondary coil, then there is a change in the flux linkage. Okay. We don't have to use a ferromagnetic moving element in this case. So now the moving elements are the coil, okay, the coil. Okay, so it is used for angular displacement. The rotor contains the primary coil, okay, consists of single two-pole winding element energized by a power supply. Usually it's a AC power supply. A rotor is the primary, okay? You attach to the object. So you want to measure that object's angular displacement. In this case, the stator Usually you have a set of windings placed 90 degrees apart. Okay, so it's called quadrature configuration. Quadrature. Okay. Let's see the picture. Okay, let's see the picture. So we should know that the resolver, I personally never actually used the resolver before. So it is high accuracy, fine resolution, of course. It's analog, okay, remember. It's low output impedance, high signal level. The signal level is high, small in size, simple and robust. So all these are good things. And that means it's expensive, okay? The output signal could be nonlinear, okay? And the bandwidth is limited by the power supply frequency, okay? And you need a slip ring and a brush. So this is a weak point, mechanically weak. So let's see it this way, okay? So basically you have a rotor, okay? On a rotor, you have an AC power supply, but you have a stator here not changing. So if you move, okay, if you move, the theta changes. So you are going to see that the coupling of the rotor and stator coils are different. Okay, so then they will produce the voltage, which is cosine theta. So when you have a cosine theta, then I know that cosine theta is like a theta as well. Okay, so it's also a linear relationship when theta is small. Okay? And so that's for resolver. Then self-induction transducer in the principle of self-induction. Okay, so it's not like a mutual induction is you have two coils. Okay, so you only have one. Okay, you only have one. So let's check one of the examples here. Okay, so this is another type of not mutual. Okay, so we just have seen a mutual inductance, but now it's a self-inductance. So you have power supply to this one, and so then inductance measurement circuits. So to measure the inductance change. So this is a ferromagnetic target movement. So you can this target, if you change, okay, if you change, then the voltage you get here is also changing. So this is called self-inductance proximate sensor. There are also permanent magnet in this case, okay, permanent magnet. So most useful one is the permanent magnet speed transducer, which is called tachometer, okay, tachometer. Tachometer is used to measure the voltage, which is proportional to the speed, okay. So this is another idea of permanent magnetic transducer. So you can do a rectilinear velocity transducer, or you do a DC tachometer generator. So there are two. So this is A. So you have a linear motion, okay, for this bar, okay. For this bar, you have linear motion, okay, go this way. So your voltage coming out of the coil attached to the moving coil. Because you have a magnet, you have a permanent magnet. This is a permanent magnet in this coil, okay, in this coil. So if you pull out, it's basically you have cutting the flux, okay, cutting the flux. The coil cutting the flux will produce the output. The output is proportional to how fast you move. So that's called linear velocity transducer. There's another way, it's easier. We are going to explain next week about DC tachometer generator. So actually, we should say it is generator. It is just a generator, okay? How to generate the DC. So easy, you have a permanent magnet PM in here. So this is a PM, permanent magnet. One is N, one is S, okay? Then in the middle, you have a armature is a rotor. Okay, so the rotor is connected to your the speed of shaft. You want to measure the speed. Okay, so if we put so these are the coils. Okay, so these are the coils. So this is the rectangular coils like this. So you turn this way, you cut the flux, then you are going to generate voltage. Okay, generate the voltage. But there is a called commutator here. This is a commutator. So to change the flux. Otherwise, your signal is if you don't have a commutator, your flux is like this. When you turn, it's become a sinusoid. Okay, become a sinusoid. But with the commutator, your signal will still be like this, but they can turn this one to this. So this is after you have the commutator, okay? Commutator. So your waveform is like this, okay? But you say, is this a DC? It's not a constant, right? But remember, you have the signal. So if in here, your signal looks like this, but if you put this one into a circuit, and inside this circuit, you put like a RC here, okay? Then you check this point, what is the waveform? So let's use the black. So what is the signal in here? Okay, the signal in here. So I tell you, the signal will be like this. So this is almost like they will filter all those high frequency out. So leave all this. So or more or less like straight line. Okay, more or less straight line. So that's more like a DC. Is that right? So that's how they make the DC. Okay. So for the DC generator, we are going to focus on this one next week to explain it in a more detailed way. Okay. But if you want to watch the YouTube, I think you will find out many of those the operational principle of DC generator. Okay, DC generator. Another type is called AD current transducer. Okay, AD current transducer. If you have a conducting medium, okay, conducting medium, you have a fluctuating magnetic field. So then you will be able to generate the AD current in the medium. The strength of the AD current increases with the strength of the magnetic field and also the frequency. Let's check this. This is all the explanation of this figure here. Okay, this is called AD current proximate sensor. Okay, so basically it's just like a pen. Actually, it's like a pen. So you have a conducting surface, like a patch you put on the surface. Then if my pen is closer to this, then I will generate larger signal. Okay, so how to do that? It is because you have an active coil in here. So then you have a radio frequency converter to have a power supply. Then you have a very high frequency, usually that's a megahertz level, like 100 meg. Because of that, you have this magnetic field generated here. Okay, so if the distance is different, then the strength of the AD current will be different as well. So then you can read out the outputs. Okay, that output signal will be proportional to the distance. Okay, for distance. So this is called AD current proximity sensor. So of course you need to have you have other bridges about impedance, okay, to get out the impedance. So this is like the circuits. It's like the bridge circuit is in here. RF, the generator is 100 meg, remember? Megahertz. So you have this one, then we'll produce the impedance everywhere, okay? So you have an active coil, you have a compensating coil. So then the active coil is in the front. Then you have a different distance, you have different inductance. So therefore, we can have a bridged output. So this output will have also a very high frequency here. You need to have a demodulator, meaning I remove those carrier frequencies, okay? Carrier frequencies. Then we can send this, we can send this one to the denominator to remove those carrier frequencies. So something like this. So you have a signal, right? But on top of the signal, there's a very high carrier frequencies, okay? Carrier frequencies. So this is called modulation. Then demodulation is to remove the blue. The blue is removed, okay? Blue is removed. Then we put this, we get a red signal out of it, okay? So this part is not the emphasis, okay? It's not the emphasis. We just know the working principle is fine, okay? And any questions for this part? We're going to finish this analog motion sensors, okay? All right, so you can see that for Mechatronics system, the analog motion sensors are the basics. I think one of the important thing we emphasized is the sensor specs. Do you guys still remember the sensor specs? 5 important ones. Okay, first is the frequency range of interest. Okay, then the frequency range of interest, like what's the range or what's the frequency range it can work, and output impedance and resolution, accuracy, and sensitivity. So I hope you will go back to the textbook, find out the definite definition of this one, okay? If I want you to explain to me what is the resolution, what is accuracy, what is sensitivity, you should be able to answer this question, okay? Okay, so we have spent a good time on this one. It's time to look into optic encoders, okay? It's mainly focused on measurement of it's mainly focused on the measurement of angular displacement, okay? Okay, so it is usually in a digital form, okay? Digital form, okay? Digital form. So digital means binary, okay? So depends on how many bits you are talking. So you have 12 bits, then it's 4096. So if you have 360 degrees for one round, so you can see it's actually very accurate. It's about 0.1 degree. So it could be very high resolution, high accuracy, and also noise immune, meaning it's digital signal. Some little bit of noise will not affect our counters. Okay, so it is a coded reading. Coded reading. So this is important term. Coded reading. It's called encoder. Encoder means you put it like a code. So it's a digital transducer. So we're going to see is this encoding There are multiple ways to encode. So the optical encoders is only one of them. There are other ways to do this encoder. We are going to focus mostly on the incremental encoder because it's cheap, low cost, and high accuracy. And so there are two types. One is called absolute encoder, one is called incremental encoder. We are going to learn this, but we put more efforts on incremental encoders. So what is an absolute encoder? Okay, we're going to see an example of that. Okay, that's probably easy to take a look of a picture here. Okay, suppose you have a disk. This disk is opaque, not transparent, but they open those windows. Okay, these windows are called slits. Okay, slits. Those windows are transparent. So I have a pickup point in here. Pickup point. This could be a receiver of a light sensitive, like a photodiode or phototransistor, even photocell. So if you have a light coming, I'm going to generate a signal. If you blocked, there's no current, then I'll come to zero. If I have current, then I have this. So as I move, as I rotate, then this output will generate a trend of this pulses, okay? High, low pulses. Okay, so that's the basic principle called optical encoder. So this one circle of the physical, I call this physical windows. This one is called one track. Okay, it's one track. Okay, and you have pickup point here. It's only one pickup point. Okay, one pickup point. But what if I put more than one pickup of pick off sensor? What I have two, then I have two channels. So this is one channel. This is one channel of the signal. What if I have another channel, another pickup point with another light source? Okay, it's also possible, right? Yes, it is possible. So on this disk, okay, so if I look at this disk, I may have multiple tracks. So I have multiple tracks with different transparent windows coded in such a way. So let's go back. So we just put in this. So this is just one. Oh, if I put the dark black one as not transparent, the white one is transparent, okay? So the white one is transparent. I put this is called a coded disk, okay? Okay. For each of this is called a segment, okay? So concentric is a track. So how many tracks, okay? And a segment for each tracks. So for each of these one, for our case, we have 16 segments, okay? 16 segments in our case. How many tracks? 1, 2, 3, 4. I have 4 tracks in this case, right? So of course, you have many ways to make this disk, okay? Giving 4 tracks, giving 16 segments. So you have all different types. Or one is this one, another one is this one, okay? So for A, this one is called binary code. Why? So you can see we go from here. If, let's see, if we say the dark is 0 and the white is 1. So this first one is called, this segment is called 0, 0, 0, 0. Okay, so 0, 0, 0, 0. Then the next one is 0, 0, 0, 1. That is this segment, okay? And the same thing is true. So this is 0, 0, 1, 0. Okay, so this is called binary code. And the next one is 0011. Okay, 0011. So you can see each one is like add one, add one, add one, right? So add one. So the absolute value of this 4-digit, okay, will like sequentially like 0, 1, 2, 3, 4 until this. So this is called coded disk in a binary way. It's called a binary code, okay, binary code. But there are many other ways to do this type of coding. One of the idea is to do a gray coding. So what's the difference? Okay, what's the difference? So we're still starting from here. They do 0, 1, 1, 1. This is the first, okay? 0, 1, 1, 1. This is the corresponding to 0, okay? And 0, 1, 1, 0 is corresponding to 1. And this is 0, 1, 1, 1. Oh, sorry, 0, 1, 0, 0. Okay. Okay. So did you observe anything different? So from here to here, there's only one bit change. Okay, there's only other three are the same. Okay. So there's only one bit change from 1 to 0. Okay, those other three will not change. And from this one to this one is also three of them are not changing. So only this one goes to 0. Okay, other three are not changing. So every time I only have one bit changing. But be careful, you look at this one here. So you have bit changing here, you have bit changing here, you have two changes in bits, right? Actually, it's not desirable. I hope every time I move one segment, I only have one bit is changing. So this is called gray code. Of course, they can be, they can transform to the original one. There's a one-to-one correspondence. Okay, it's called gray code to binary code conversion. So why we do that? Why we do that? This is because the coded disk is only one bit change. So the whole reliability is much higher. Okay, the chance you get error is much slower than the binary code. Get sense? All right. So okay. So this actually you have a multi-segment. You have a multi tracks. So this is called absolute encoder. Okay, absolute encoder. Absolute encoder. So for you, you go to any place, any angle, then your angle is different. But if you need 10 bits, okay, now I have 4 bits. Okay, it's 4 tracks. So if you need 10, you need 10 such tracks. Okay, then that in disk is hard to make. It's more expensive. Okay. So that's an absolute encoder. Absolute encoder. Okay. So by using this optic encoder, you have multiple tracks and a multiple pick-off sensors. So you need corresponding to different tracks, you have different sensors. Okay, different sensors. So if you have 10 tracks, you need 10 sensors. You have 10 channels of signals. Then together, you define very uniquely of your absolute position all the time. Okay, so this is called absolute encoder. They're still being used widely in some high performance systems. Okay. On the other hand, there are other ways to do this encoding process. I said encoding, you can do optical way. I give you an example that is not an optical wave. It's called a magnetic wave. Say, for example, okay, so you have a electrically insulating materials. This is a cold disk. You put some windows, but these windows are actually conducting dots. Okay, these are the conducting dots. Okay, so then this is a commutator brush. So you contact with this. So if you go to here, this and this is not contacted. If you go to this contacted area, it's like a window. So this is a circuit is connected. So you got a very interesting pulse like this. So this kind of using a magnetic way for the contact, not optical way, is also sometimes used. Okay. All right. So tracks the same as channels. Yes, for each track you have a channel. You need a readout. Now we are talking about it's possible for if you put more than one readers for one track, that is also called a channel. Okay, so this is what we have learned. This is transformer pickup element. So if you have a rotating disk, then the magnetic reluctance we experienced will be different because the media is different from magnetic area or non-magnetic area. Okay, so this is also a pulse. We can convert this analog signal into a digital signal by certain demodulation, demod circuits. Okay, so this is using a magnetic mechanism for encoding the signal. Sometimes this is still being used. Okay. Also, people use proximate sensors using a magnetic induction. Okay. Induction means self-induction. Okay. And we have learned this proximate probe idea. So the same thing, we can get a different waveform like that. Again, you need a demodulation. So you can get some pulses like this. But I never used this type of sensors before, but you should know. Okay. So you should know that optical is today more popular is because it's widely produced and it's cheaper. Okay. So the basic idea is in this figure. Okay. This is called incremental optic encoder disk. Okay. In this case, to reduce the cost, there's only one. Okay. Only one track. Okay. Only one track. All of these windows, all these slits. Okay. So all these slits, there's only one such circle. Okay. So therefore, it's difficult to tell absolutely where you really are. However, if I put the index, okay, you put like a reference window, I put something here, okay, then it will be able to tell how many pulses since that pulse, okay. Also, they do two pick-off heads, okay, like you put different positions. Okay, different position. There's some phase difference. Okay, this is actually a called quadrature arrangement. I'll show you next. Okay, so you can see this code disk is obviously much cheaper than this one. This one is complicated. It's expensive, right? So, all right. So this is the one we are going to focus: incremental optical encoder disk. Okay. So as I have seen there's questions about how many channels from the readings. If you have two pickups, so then you are going to have two channels read out. You have two channels. Okay, 2 channels. And so then you also have an index pulse. Okay, index pulse. So this is a typical signal. So channel 1 and channel 2. Okay, channel 1 and channel 2. Okay, so if you move clockwise rotation, so you will know that V1 will lag V2 by the lag of 90 degrees. Okay, so in this window, you can put a pickup 1 in here and 1 in here. Okay, so there's a phase difference. So based on this phase leading or phase lagging, you will be able to tell you are rotating counter clockwise CW or counterclockwise CCW. Okay, so you will be able to tell. Okay, and after we have also we have a points in here. So if I see one pulse in here, okay, I know this is one revolution. If I see another pulse in here, this is another revolution. Okay, so this is revolution K. This is a revolution K plus 1. Okay, so this pulses is an indicator how many pulses, how many revolutions, and in between here we count how many pulses we see. Okay. So how we can tell how much we moved? Okay, how much we moved. So we assume that a maximum counts possible is m pulses for one revolution, and the range of the encoder is plus or minus theta max. Okay, theta max. The data size are bits. So the meaning how many bits, how many pulses you will have. Okay, so usually this is an integer like 10. Okay, 2 to the power of 10. So 10 minus 1 is 9. 2 power over 9 is 512. 2 to the power of 10 is 1024. Okay, so you may wonder why I remember this. Yeah, it's easy to memorize all of this. Because when I was a student, we usually learn 8 bits. 8 bit is what? 256. Okay. So usually we allow this shaft to continuously rotate. So we would like to say theta max is 2 pi, theta means 0. Okay, so theta max and theta mean are the same. Okay, the same, but they are different to this. The total number of pulses 2 to the power of r minus 1, which is m. This is m. Okay, total number of pulses per ref. Okay, so the digital resolution is like 360 degrees versus 2 to the power of r minus 1 minus 1. So that is the how many degrees of the resolution. Actually, resolution is something like this. So if the angle is smaller than that, I cannot see it. I treat it as a 0. Make sense? Okay. So say for example, you have a ruler with this as your say for example, like this is mm, 1 mm millimeter. This is 1, 2, 3, 4. So what's the resolution? You can actually read it as a half or 1/10. So I think the 0.1 will be below 0.1. I really should treat to 0, right? So there's a resolution there, okay? Resolution that minimum value that I should treat it to 0. I cannot distinguish anymore. So this is exactly the meaning here about resolution. It all applies to analog and digital sensors as well. So now I know how many pulses corresponding to how many degrees. Then I want to understand how fast I'm rotating, the angular speed, angular velocity. So one of the ideas is to pulse counting. Some people also use pulse timing. If you have a timer, you can trigger that timer. Okay? So the pulse count over sampling period, okay, of digital processor is measured and used to calculate the angular velocity. So it's usually called pulse counting method. Okay. But if you do that, there's a lower speed limit below which the method is not accurate. It's like noisy, okay, noisy, because it's at that quantization, what I would call quantization level. Meaning, so you have number here, or you have number here, or you have number here. Basically, these are on the same position. So it's within the quantization level, meaning that digital resolution level. What's in between is not sure. So then your voltage will jump up and down, up and down, up and down, right? Okay. Okay. So there is a inaccurate limit of the speed. So if your speed is high, it's fine. If your speed is very low, then it's not very accurate. So angular velocity, we have a count during the sampling period is T is n pulses. Okay, the average time for n pulses is T divided by n. That's 1 pulse. You have n windows on the disk. Average time for 1 revolution is n times this one. Okay, so the omega is like a 2 pi. Okay, and what 2 pi f. Okay, 1 revolution average time. Okay, so it's 2 pi divided by t is omega. So t is nt divided by n. So it's a 2 pi n divided by nt. Okay. So that's simple. For pulse timing method, you need a timer. Okay. So if you use a very high frequency clock signal, so it's suitable for lower speed accuracy. So if you want to measure speed accurately, the pulse timing method is better to be used. Okay, so remember that. Okay. So you have a clock frequency, yeah, clock frequency. You have m cycles of the clock counted during the encoder period. So that you have 2 windows adjacent, then you can count how many clock pulses. So the time for that encoder cycle is limited by actually your clock frequency. Okay, if your clock frequency is high, then I can count it very accurately. Okay. So if I have n windows of the track, average time for 1 revolution is n times n windows. Each window is m divided by f. So the omega will 2 pi f divided by nm. So that's why if f is high, then the resolution is high. So you can do better. So here, there's the implication here. So you have a clock pulse. You have a very high frequency clock pulse. And you count this clock pulse based on your the window, okay? If your window is high, I start to count. If your window is 0, the signal is 0, then I stop counting. So this is called a counter. Actually, it's a timer. Okay? Timer is also counter. Okay. There's also a smallest number of unit of the time. That's called a clock. Okay, the clock. So you use that clock circuit to do the counting. But today you don't have to worry too much about this. This already has encoder chip to do the work for you. So, but you should know that in principle there are two types of velocity computing. One is by counting pulses, another one by timing the pulses. Okay, timing the pulses. Pulse timing, pulse counting, two methods. Regarding the resolution, okay, of encoder, okay, so we have one question in the quiz about why it is by the time of 4. I'm going to show you. So resolution of encoder, okay, the smallest change in the measurement that can be measured realistically. In other words, there is a minimum threshold. Below that, you cannot see it or sense it. Don't dream about it. It's beyond physics, okay? So I like the realistically. So what is the displacement resolution? Okay, listen carefully. It is not only by the number of windows. These windows I call physical windows that put on the disk, okay, in the code disk. Also about digital size, a number of bits of the buffer or counter output, how you count it. So the physical resolution is determined by n, but only one pulse signal is used. Okay, no directional sensing, no quadrature arrangement, just one channel. But if the rising edge of the pulse are detected and the full cycle of the encoder are counted, the physical resolution is only like 360 divided by n. So we know that that's easy. Okay, this is physical resolution. But if we use quadrature signal, meaning I have a window in here, I put a one pickup point in here, another pickup a sensor in here, okay, with this distance. So there's a phase shift between them, okay? So then I get these two channels, okay? So we both detect the rising edge and falling edge. So I detect this edge. I also detect this edge, okay? This edge, the rising edge and falling edge, okay? All right, so then actually I have two channels. I have 4 counts. I have 4 counts because of this rising and going down, okay? Per encoder cycle. So in that sense, we actually physically, it's not just fixtures, it's real. You can improve in the resolution by a factor of 4 because this is the one, then you have another signal. So you also have up rising edge and falling edge. So you have 1, you have 2, you have 3, you have 4. So this all can be used. Okay. So in that sense, it's a 360 degree and 4n. Okay, 4n. So now you understand. Okay. So assuming the maximum angle is 360 is 1 ref. It's 1 ref. Okay. 1 revolution, 1 ref. And so the digital resolution is given by this, okay? Digital word containing R bits can be represented by 2 to the power of R different values, without a sign, okay? With unsigned means without plus or minus, okay? either plus or minus. So in other words, you have 0 and 360 is the same position. So you may have ambiguity, okay? And so you should distinguish this, okay? You should distinguish this. So the larger the two resolution governs the displacement resolution of the encoder is this number of physical windows n times 4, okay, times 4. Okay, so the physical resolution of encoder is improved by the stepping up gearing. So one rotation of the moving object is being monitored corresponding to, you have several rotations in the code disk. So it will improve our resolution a lot, okay? Okay. So in summary, this displacement resolution incremental encoder depends on the following factors: number of windows on the code disk. You also have gear ratio, but in our case, we always assume here is 1:1, don't consider, and word size of the measurement buffer. So that kind of quadrature, so you can see for each cycle, we have 4 different, so V1 and V2 together, we have this type of waveform. So this is called quadrature signal to improve the physical resolution by 4. Okay, it's because of that. And velocity resolution is usually the T is the sampling period, number of windows. Okay, so this is 2 pi divided by NT is my smallest omega. I can check doing a pulse counting. Pulse timing is depending on the clock frequency. Okay. Okay. So it's n is the number of windows times this m. Okay. And so here, speed resolution depends on the windows, sampling period, clock frequency, gear ratio, and your actual speed. So the speed resolution is a little bit more complicated than the displacement. Okay. So the shaft encoder readings, you have some error sources, like quantization error. This is due to the digitization. If you have a little bit is not aligned well, it's called eccentricity. And sometimes the coupling of the gear through the gearbox, you have gear backlash. You have a belt connection. It's a slippage in the belt and so on and so forth. So this thing should also be careful. Coupling error, assembly error, and quantization error. In practice, you should consider all 3, but in the design phase, usually only consider this quantization error, like number of windows you may have, structure limitations, and so on and so forth. So at this point, I think we got enough about digital encoders. So let's see what you can do for your this one, okay? So this is a real encoder. This one you have learned it, right? Do you know how to do this now? You should, okay? I already explained in the last lecture. But here I want to make some, I give you, so you can see usually you have 5 pins, okay? You have channel A, channel B for those 1 track of windows. Then you have another channel I, meaning index. That's like how many revolutions you 1 revolution, 1 pulse, 1 revolution, 1 pulse. Okay, channel A and B. So you have a VCC is your 5 watt, you have GND ground. Okay, so you hook up this one attached to the X the shaft, okay, align well with it. So the shaft move, this one will also move. There's no mechanical friction. It's optical, so it's effective. But remember, you have this 5 watt. You have R in here is a 2.7 kilo ohm. So these resistors has a name. It's called pull-up resistors because these signals are supplying outside to other processing unit. They may not have enough the logical level. Okay, so we provide this pull-up to provide if needed, so they can provide enough current. Okay, enough current. So in this case, the resolution is 500 pulse per revolution, and the resolution with quadrature is 2000. So this is 4 times. Did you see that? So basically, you have 2 pickups. Therefore, you have channel A and channel B signals. Okay. So this is a specific incremental optic encoder. It's called 5-wire pinouts. So this spec is 4096. Looks like the one show this. Okay. Then we want to understand how many transparent windows physically on the disk inside the encoder. What you should do? You should divide this one by 4, right? Divide this one by 4. I didn't say this is the same, but I just say that you have counts per second. Counts per second is like this, pulse per revolution. So counts per revolution, okay? CPS, counts per revolution. So you have 4096. So how many windows divided by 4? So 1028. Is that right? Divided by 1824. So the answer is 1024. All right. So we can finish here to see whether you have some suggestions and questions. Starting from next week, we are switching to to the actuators. Okay, actuators. So this week and last week we started sensors, mainly focused on the sensor principle, and then analog sensor, and then digital sensor. That's it. So, well, we have 3 minutes over time. All right, I'll see you next Wednesday. Have a good weekend, everyone. All right, bye-bye.